welcome to the 32nd lecture of combinatorics. So, we continue with what we stopped in the last class. We were describing recurrence relation involving two sequences of numbers A1, A0, A1, A2, A3 etc. and another sequence B0, B1, B2, B3 etc. The recurrence relation for A so is given say n plus 1 not only in terms of the some previous number in the A sequence, but also some number in the B, something this is 1 and then okay. And another thing is this one Bn plus 1 is equal to An plus Bn. Now, Bn plus 1 is expressed both in terms of An and Bn, right. Now, how do we solve this kind of recurrence relation? So, to illustrate that we have taken this example. So, we summed it from n equal to 0 to infinity here. So, that means everywhere we have to sum. Sorry, first we multiply this by x raised to n plus 1 everywhere, x raised to n plus 1 everywhere, and then we sum it n equal to 0 to infinity. So, that means here also we sum n equal to 0 to infinity, and then this becomes because this n equal to 0 to infinity, that means n plus 1 starts from 1 and goes to infinity. So, that therefore, this is not really a of x, but it is a of x minus a of x minus a0 into x raised to 0, but a0 is given to be 1. So, it is 1 into x raised to 0, that is just 1, right. So, we get 1 here is equal to here what happens is 2 we can take out, here n equal to 0 to infinity, but x raised to n plus 1 is multiplying. So, we can just remove this and take x out, right. So, 2x comes out, and then it is from n equal to 0 to infinity a n into x raised to n, this is a of x, right, plus here we can take again x out here, x can be taken out. So, x into b of x, this is one thing we get. Now, we can rearrange this as we mentioned yesterday to get see the one you take to this side and all ax and bx to this side. That means 1 minus 2x times ax, 1 minus 2x times ax minus x times bx is equal to 1. This is the first equation we get, right. And same way we did for the first recurrence relation, we can do it for the second one, Bn plus 1 equal to this one, Bn plus 1 is equal to An plus Bn. So, what do? You multiply by x raised to n plus 1 everywhere, and then sum from n equal to 0 to infinity, 0 to infinity. Same arguments. So, because now this is b of x minus b0. So, that will be b of x minus b0, b0 was equal to 0, therefore, this is just 0, and then here we can take x out, and that makes x times a of x plus here we can again take x out, x times b of x will come. Now, we can rearrange. So, we get x times a of x plus x minus 1 times b of x equal to 0. This is the second equation. So, this and this together, so we have to solve. So, we have to get an expression for a of x and expression for p of x. For example, first you can try to get rid of b of x, say you can multiply this by x minus 1, this by x, and then add them together, then bx will disappear and then we can solve for a of x. Similarly, then after getting a of x we can solve for b of x. So, I will leave it to you to figure it out. So, that way we get the generating function for a of x as well as b of x, right. So, this is this solves that. Now, we will go to a different kind of generating functions called the exponential generating functions. The ordinary generating functions that we were considering up to now are suitable for counting problems where involving just selection, while here these exponential generating functions will be useful, as we will soon see, in cases where we are counting things where order matters, right, the order matters. So, let us introduce the exponential generating function like this. So, suppose your sequence is A0, A1, A2, etc., 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 and then we write the generating function f of x equal to A0 plus A1 times x plus A2 times x square by 2 factorial plus A3 times x cube by 3 factorial and so on, and this generating function is called the exponential generating function for the given sequence. Once again, see again, our sequence is A0, A1, A2 and so on. So, note that our ordinary generating function will be A0 plus A1 x plus A2 x square plus A3 x cube and so on, and the coefficient of x raised to n will be a n. Here the difference is that the exponential generating function is A0 plus A1 into x by actually 1 factorial plus A2 into x square by 2 factorial plus A3 into x cube by 3 factorial and so on, right. So, for a n will be the coefficient of x raised to n by n factorial here. So, that is the difference. So, this looks like a little strange to begin with, but you will see soon that this is useful in solving certain problems. But some examples we can easily see. Suppose the sequence is 1, 1, 1, 1. This is the most familiar sequence for us. So, A0 equal to 1, A1 equal to 1, A2 equal to 1 and any an equal to 1, right. For this sequence the ordinary generating function is what? It is just 1 plus x square plus this one, right. This is 1 by 1 minus x, right. We have seen this before. But the exponential generating function will look like this: 1 plus x square by 2 factorial plus x cube by 3 factorial and so on. From calculus we know that this is e to the power x, right. So, the exponential generating function for this sequence, so whose ordinary generating function was this 1 by 1 minus x, is going to be this e raised to x. Another example is, what about 1 plus x raised to n, which is, what is that? 1 plus x raised to n is another familiar generating function for us. 1 plus x raised to n, this is n choose 0 into x raised to 0 plus n choose 1 into x and so on, right. So, this is the generating function for these numbers n choose 0, n choose 1 and n choose I, right, this sequence of numbers. So, n choose n, after that n choose n plus 1, which from there onwards it is 0. So, but this, in other words, this 1 plus x raised to n is the ordinary generating function for this sequence of numbers. So, then it is the exponential generating function for another sequence of numbers, which is that sequence of numbers. So, in other words, if I want to write 1 plus x raised to n as some a0 plus a1 x plus a2 x square by 2 factorial and so on, then what should be this a1, a2, a0 etc., that what should be ai or an, say, right. See, you can easily see that it is n p r, right, n p r. Why is it so? It is because, you know, you put here, if you put np2 by 2 factorial is going to be nc2, which is the actual number which should be the coefficient of x square here. For x raised to n, the actual coefficient is n, sorry, not an ar, I am saying ar should be npr, right. So, the for instance, when I consider the coefficient of x raised to r, that is n choose r when you expand this stuff, right. Now, but I am only interested in the coefficient of x raised to r by r factorial. So, that means this is n factorial into n minus r factorial into r factorial. This r factorial goes here, right. I am only interested in this part, and this is actually npr, right. So, therefore, we see that 1 plus x raised to n is the exponential generating function for this sequence n np0, np1, np2 and so on, while it was the ordinary generating function for nc0, nc1, nc2 and so on. Then yeah, now we will look at how we can use this stuff. So, look at this question: how many ways can 4 of the letters in engine be rearranged? Four of the letters, there are 6 letters here, you have to pick up any 4 letters you like from this thing, and then you want to permute them, arrange them in various ways, order them in various ways, permute them. The point is, you can pick up possibly these 4 letters and then you can do it in 4 factorial ways, or you can do e and nn. These 4 letters you can take out of that, and then now you do not have 4 factorial, actually 4 factorial by 2 factorial into 2 factorial ways of ways are there to permute these things, because 2 letters here are same, 2 letters there are same. So, we have studied how to count this thing, because initially we will think that all are different. So, this is an E1 and E2 and this is an N1 and N2, and then we have 4 factorial ways, but then now E1 and E2 actually one and the same, therefore, we divide by 2 factorial, because among them you can permute in 2 factorial ways. Similarly, n and n, so n1 and n2, it is just n, so therefore, we will divide again by 2 factorial, right. So, and again there are many other ways of selecting 4 letters from these 6 letters. So, you could have taken E n n I. So, now this is 4 factorial by 2 factorial, because this repeats 2 times. So, now finally, the answer we seek is the sum of all these things. First select 4 letters and then consider how many ways they can be permuted and then add them together. How many will be there. So, this is where we are going to use exponential generating function for counting. So, what we do is, we will introduce one term for each of the letters. There are this many letters. One letter is E, another letter is N, each type of letters, let us say, and another is G and another I, engine. So, since there are 2 E's, we can either not take any of the E's in our, we are picking 4 letters out of those 6 letters, we may not select any of the E's, right, that means 1, that means x raised to 0. So, or you may select just one E, or you may select 2 E's. This is the term we introduce for E. This corresponds to the terms 2 E's. Okay. And now for 2 N's also we can have one such term, 1 plus x square, because you may not select any of the N's in the 4 letters we pick up from this thing, or we may select 1 N, or we may select 2 N's. And for other letters G and I, which appears only once, we have only 2 choices, either we may select or may not select, this way. Now, we claim that, so let us say this is f of x, we claim that this f of x is indeed the exponential generating function for the count we are looking for, which essentially means that we are looking for in how many ways 4 letters can be picked from the 6 letters available here and permuted, arranged, right. So, we are saying that okay, if you are looking for picking the 4 letters case, then you just have to consider this thing, and you just have to consider the coefficient of x raised to 4 by 4 factorial, the coefficient of this in f of x, then you will get the answer. For if you are only talking about picking 3 letters from this thing, then probably you just have to look at, so then we mean that we have to look at the coefficient of x cube by 3 factorial, x cube by 3 factorial in f of x. In general, if you are looking for picking k letters, then x raised to k by k factorial coefficient is what we are looking for. So, that way f of x is going to be the generating function for this count, the sequence of numbers defined by the kth term of the sequence being the number of ways of permuting the letters after selecting k letters from this, right. So, now how is it true? That is what we are asking, right. Now, I will try to explain this. Why is it so? Because see, for instance, in the case of 4, x raised to 4, how can you get x raised to 4 from this thing? Sorry, here I have to, because exponential I have to put this, sorry, it is a mistake. So, because we are talking about exponential generating functions, when we take this thing 1 plus x square by 2 factorial, so that is all. Now, we have to find the coefficient of x raised to 4 in it. So, what are the possible ways to get x raised to 4? Definitely we have to select something from here, something from here, something from here, and something from here to make x raised to 4. For instance, if you take x square by 2 factorial from this thing and x square by 2 factorial from here, then you have to take 1 and 1 from here, because x square plus x square is already x raised to 4, right. So, that would correspond to selecting 2 E's and 2 N's and no I's and no G's. On the other hand, if you had picked up x from here and x from here and x from here and x from here, it would correspond to selecting 1 E, 1 N and 1 I and 1 G. So, that is all various possibilities, all possibilities of making x raised to 4 will correspond to how you select the letters from this thing. Now we have to also incorporate the fact that we have to permute them, right. So that is where we are looking for. For instance, let us look at one selection. For instance, 2 E's are selected, that means this term comes from here, and 2 N's are selected, that means this term comes here, and here it is a 0, this is a 0 I and 0 G from here, 2 E's and 2 N's. So what in the product how we get is not directly x raised to 4, we get x raised to 4 by 2 factorial into 2 factorial, because here we are getting x square by 2 factorial, here we are getting x square by 2 factorial, this is what we get. But then what we are looking for is the coefficient of x raised to 4 by 4 factorial. What we have got is x raised to 4 by 2 factorial into 2 factorial, but where is this 4 factorial? So what we do is we convert it to that form. So we write this as x raised to 4, so this is a 4 factorial introduced here, and 2 factorial is kept here, but to cancel this I will put a 4 factorial here. So we have a x raised to 4 by 4 factorial. The coefficient is 4 factorial by 2 factorial into 2 factorial, but we know that this is exactly the number of ways to permute this 2 E's and 2 N's, because there are 4 letters that correspond to 4 factorial. This 2 factorial comes twice because there are 2 E's and 2 N's here. Now the same way for any possible selection. So to make the x raised to 4, you may take 1 from here and 2 from here and 1 from here, say, and nothing from here. That means an x comes from here, and x comes from the first term, then x square by 2 factorial comes from the second term, and x comes from the third term, and 1 comes from the last term. This corresponds to 1 E, this corresponds to 2 N's, this corresponds to an I, and this corresponds to a G. Sorry, this corresponds to no G's. There is nothing, because here 1 means x raised to 0. So the selection is, the selected letters are E, N, N and I. Now we get not x raised to 4, we get x raised to 4 by 2 factorial. But we are looking for the coefficient of the x raised to 4 by 4 factorial. So therefore we introduce 4 factorial above and below, that means in the numerator and denominator. So and then this will look like this, right. The coefficient of this thing is 4 factorial by 2 factorial, and we know this is exactly the number of ways you can permute this thing, because there are 4 letters, that is 4 factorial here, and 2 N's, therefore 2 factorial in the denominator, 4 factorial by 2 factorial. Now for any possible way, see, the selection of 4 letters will correspond to a selection of some term from here, some term from here, to make up x raised to 4. And so conversely, if you consider any breakup of x raised to 4 as some term from here, some term from here, and some term from here and here, that will correspond to a selection of 4 letters from here, right. And somehow by looking, by putting see this 2 factorial in the denominator, whenever we are selecting 2 letters, so we also have the 2 factorial coming in the denominator in the product, right. Now because we are interested in the coefficient of x raised to 4 by 4 factorial, we can introduce a 4 factorial in the numerator. So that 4 factorial in the numerator and the corresponding 2 factorial, how many, now it's depending on how many times that x square was taken, we get so many 2 factorials in the numerator. That counts exactly how many ways you can permute those things, selected letters, and we add them up all. That will be the final coefficient of x raised to 4 by 4 factorial. The final coefficient of x raised to 4 by 4 factorial will be this plus, yeah, for each of them. So this plus, so this was, sorry, this was one, and this was another, like that. For each selection we got some term and we were adding up, right. So, therefore, in the exponential generating function f of x, the coefficient of x raised to 4 by 4 factorial will turn out to be the number of ways of first selecting 4 letters and then permuting them. How many ways you can permute after selecting 4 letters, right? Select any 4 letters and permute them, count the total orderings of selected some 4 letters selected from the 6 available letters. So, this is how the exponential generating function work, right. So, you should note that the fact that we are looking for the coefficient of x raised to 4 by 4 factorial was very crucial here. That is how we got that 4 factorial in the numerator all the time. So, that is how we could ensure that we are actually getting that count of the permutations of those 4 letters we selected each time. Now, let us take a new example which will make things clearer. So, a ship carries 48 flags, 12 each of the color red, white, blue and black. That means, we have 12 red flags, 12 white flags and 12 blue flags and 12 black flags. What they do when they want to give a signal to another ship which is coming near, they will use 12 of these flags. Out of these 48 flags, they will take some 12 flags and arrange them in the flag post in so maybe it is like this. They will select, suppose they will select the flags and they will tie the flags like this here, right. 12 flags will be tied. So, this order is important here. For instance, this was a blue, these are 3 blue ones and then 1 black here and then 1 white here, right, sorry, then 1 white here. So, white, this is a black and these are blues. If you reorder them in some other way, it will correspond to another signal. For instance, you can put white on top and black later and 3 blue later in the below that, then it will give a different message, that is a different signal. So, the question is how many possible signals can be made this way. So, remember we have total 48 flags, 12 from each color, 12 white, 12 black, 12 blue and 12 red. Note that you can make a signal using only one color, because 12 flags are there of each color. Full signal can be of the same color, if that is also possible, right. Now, how many possible signals are? Always remember that we are only using 12 flags in the signal, though we have 48 flags total, right. Now, what to solve this thing, what we do is, if you had we will say we have a sequence of numbers, say A0, A1, A2, A3 etc. AI will correspond to the number of signals that can be made, provided you are using I flags in the signal, right. So, we will be interested in A12, right. So, we will get somehow a exponential generating function for this sequence, so that we can look for the coefficient of x raised to 12 by 12 factorial for the answer, right. This is our plan. So, what we do is we introduce one term for each color. First color, say white, will get this term. What is this term? This will be 1 plus x square by 2 factorial, x cube by 3 factorial and so on till x raised to 12 by 12 factorial. Now, the next one also has the same kind of term, 1 plus x plus till x raised to 12 by 12 factorial. See, this is the same problem like the earlier. We can create something like this, right. Factorial x raised to 12 by 12 factorial, multiply it out. Now you look for the coefficient of x raised to 12. So x raised to 12 by 12 factorial, that is going to give you the answer is what we are saying, because x raised to 12 by 12 factorial. So that this x raised to 12 should be formed by selecting some k1 from this, x raised to k1 from this, k1 by k1 factorial from this, and say, so first x raised to k1 by k1 factorial will be selected from the first term, which means that we are going to select k1 white flags. Then from the second term we will take x raised to k2 by k2 factorial, and then from the third term we will be selecting x raised to k3 by k3 factorial, and then we are going to select x raised to k4 by k4 factorial. So this will be x raised to 12, where k1 plus k2 plus k3 plus k4 is equal to 12, right, because we are selecting some white flags, some red flag, k1 white flags, come k2 black blacks, k3 blue blacks, this is red, okay, this is blue, this is red, sorry, this is white, red, blue, and finally black, okay, right. So therefore the total has to be 12, that is how we are splitting this k1, k2, k3. The only thing is, so we will end up, the answer will be not just x raised to 12, we will get k1 factorial into k2 factorial into k3 factorial into k4 factorial in the denominator. Now we are not looking for the coefficient of x raised to 12, we are rather looking for the coefficient of x raised to 12 by 12 factorial. To get that, we will introduce a 12 factorial in the denominator. To balance it, we will introduce a 12 factorial in the numerator. So we already have this k1 factorial into k2 factorial into k3 factorial into k4 factorial, right. This clearly is the number of ways to get the signal, provided we have decided to select k1 white flags, k2 red flags, and k3 blue flags, and k4 black flags, right, because there are 12 of them, 12 factorial comes from that, and we are dividing by k1 factorial because there are k1 white flags, etc., right. So now all possible splittings of 12, right, into white, red, and blue and black flags will correspond to some k1, k2, k3, k4, right, coming from each different term, and every time we will get the number of permutations as the coefficient of x raised to 12 by 12, that contribution to that, right. And then finally the sum of all these things will give the final coefficient of x raised to 12 by 12, and clearly this is the number of signals that we can make, because the number of signals we can make is actually first you have to decide how we are going to distribute this 12 to as to how many white flags should be there and how many red flags should be there, and then how many blue and how many black should be there, right. Then we should permute them, right, and then sum up over all possibilities of splitting the 12. So then that is exactly what we are getting here as the coefficient of x raised to 12 factorial, x raised to 12 by 12 factorial. So we will be ending up with the correct answer that way. If you are instead of 12, if you are looking for something more, then also we can get the answer. For instance, some other number we can see. that also will give you the correct thing. Now we have a different question. How many of these signals use an even number of blue flags and an odd number of black flags? It's a little tricky question. How many of these signals use an even number of blue flags, an odd number of black flags? Now we are not allowing for blue and black, we are not allowing all possible numbers. For instance, this K3, which was the number of blue bags earlier, and this K4, which was the number of blacks, has some restrictions. This K3 has to be even. Similarly, K4 has to be odd. This is the thing. K3 has to be even, K4 has to be odd. How do we find it out? So we need we will formulate it like this. It's easy because the first white flags we don't have any restriction. We will just write it as 1 plus x square by 2 factorial plus like that till x raised to 12 by 12 factorial. This is for white. And for red flags also we don't have any restriction. We will write exactly like the earlier. But now for the blue bags we have the restriction that we are only allowed to take an even number. That means we can take 1 because 0 is an even number. We can take x square by 2 factorial. We are not allowed to take x raised to 1 here because that is an odd number. We can do x cube by 3 factorial, sorry, x raised to 4 by 4 factorial. We are not supposed to introduce x 3 by 3 factorial like that, still x raised to 12 by 12 factorial. Now we can, for the odd, the last case, this is blue, this was red, okay. This for the black, what we can do is we can take x plus x cube by 3 factorial because only odd numbers are allowed, x raised to 5 by 5 factorial and so on, still x raised to 11 by 11 factorial like that, right, till x raised to 11 we can go. Now you know, because we are looking for the coefficient of x raised to 12 in the product, you know, whenever a term is coming from this, it will be some x raised to an even some x raised to some even number divided by that even number factorial. Similarly, whenever something is coming from here, x raised to some odd number divided by odd factorial. This will be the thing. The other case, other two first terms, it's okay, any number is okay. Now we can, for the ease of calculation, what we can do is we can extend it further. Instead of using up to here, we can add all the remaining terms. So first term can be added as 1 plus x square by 2 factorial into, instead of stopping at x raised to 12 by 12 factorial, so we can actually add x raised to 13 by 13 factorial and so on till infinity. Why? Because anyway this is not going to, these new terms we are adding are not going to contribute to the coefficient of x raised to 12. Suppose I pick up x raised to 13 by 13 factorial, we are already above x raised to 12. So then whatever that term we are going to produce by picking this and multiplying something from the other terms is not going to contribute to the coefficient of x raised to 12 at all. So therefore we can take it as a power series till infinity, right. We do not have to stop at this thing. Similarly for the red flags, 1 plus x plus x square by 2 factorial plus like that till infinity we can take. Similar case for the blue backs, but only thing is we are only allowing even powers, right, x raised to 4 by 4 factorial and so on till infinity, and this last one, this is x plus x cube by 3 factorial plus and so on till infinity. This we know is e to the power x, this is again e to the power x, so e to the power x. And what is this? This is actually e to the power x plus e to the power minus x divided by 2. Why is it so? And the last one I am claiming that is e to the power x minus e to the power minus x by 2. Why is it so? These two things I have to substantiate. I will just write once again what is e to the power x, that is 1 plus x square by 2 factorial plus x cube by 3 factorial and so on. Now what is e to the power minus x? This is 1 minus x, just put instead of wherever you see x, put minus x. This will be again x square by 2 factorial because that squaring kills the minus negative sign, and this will be minus, right, minus because it is an odd power, x cube by 3 factorial and then plus and then minus like that. Now you add up these two things, e raised to x plus e raised to minus x. What do you get? We get 2 into 1 plus, this will go away, but here this will remain x square by 2 factorial, x raised to 4 by 4 factorial. All the even powers will remain, odd powers will cancel off. So we can take this 2 here. So this is what we were looking at, 1 plus x square by 2 factorial plus x raised to 4 by 4 factorial. So this is this. So that is the third term for the blue, right. Now on the other hand, if we had tried to take minus here, this minus this, then what will you get? 2 into this 1 will go away, but here we will get a different thing. So 1 will go away, but rather we will get 2 minus x, it's 2 times x, then here this will go away, but this will remain, that is x cube by 3 factorial, 2 times has come here, so x raised to 5 by 5 factorial and so on. So this was the term which we got for the black flag, right. So we can take this 2 below, and that's why this term, so that's how we got this thing, right. So this is e to the power 2x, so this is what, e to the power 2x by 4 into e to the power x plus e to the power minus x into e to the power x minus e to the power minus x, which is e to the power 2x by 4 into e to the power 2x minus e to the power minus 2x. This is x plus y form, x plus y and x minus y. So x square minus y square is what we are getting. So e to the power 2x, e to the power minus 2x, right. So when you multiply this out, this will become e to the power 4x by 4, or maybe we can say 1 by 4 into e to the power 4x minus 1. That is what we got. So this is now this is what, 1 by 4 into e to the power x, a 4x expansion, 1 plus 4x plus 4x whole square by 2 factorial plus 4x whole cube by 3 factorial plus like this, and finally you have to minus 1, right. So this 1 will cancel off, right. So we will get just 1 by 4 into 4x plus 4 square x square by 2 factorial plus 4 cube x cube by 3 factorial plus so on, right. So what would be the coefficient of x raised to 12 in this x raised to 12 by 12 factorial in this thing, right. That will be 1 by 4 into, because x raised to 12 will have 4 raised to 12, right, because here when we look for at some point of time we will get some x raised to 12 by 12 factorial, here 4 raised to 12 will be there, right, and this 1 by 4, this is the thing. So, this is just 4 raised to 11, this is the answer, 4 raised to 11 will be the answer. So, that is the number of ways of getting the signal. So, number of signals such that there are even number of blue flags used and there are odd number of black flags used and no restriction on white or red flags. Total number of flags we can use is 12, right. See, of course, if you are using n flags, you can look for the coefficient of x raised to n, right. This is the way we did. Now, we can look at the other part. How many of these signals have at least 3 white flags or no white flags at all? How many of these signals have at least 3 white flags or no white flags at all? So, there is a restriction on white flag now, right. All other flags are okay. So, we only have to worry about the white flags, first term. So, we allow no white flag, that means 1 is fine. Now, this is not fine, x raised to 1 x by 1 factorial x, that because that is one white flag, that is not allowed, we need at least 3. No white flag is fine or at least 3. So, x square by 2 factorial also we cannot put because 2 white flags are not allowed. So, from here onwards we can put, and so on. The other things we do not have any restriction, we allow all possibilities. So, there are 3 terms like this, 1 for red, 1 for blue, 1 for black. You see, we are not restricting up to x raised to 12 alone, because it does not matter, we can take x cube onwards also, x13, x13, x14, etc. Because you know, when you are looking for the coefficient of x raised to 12, the contributions will be from only the first 12 terms from each term, because first 13 terms till x raised to 12, right. Because x raised to 13, once you take from any term, then it is already more than x raised to 12, and then how can it contribute to the coefficient of x raised to 12. So, we can without any problem we can take the infinite series, the power series we can take, rather than just restricting it up to x raised to 12 by 12 factorial, right. So, we know all these things. This is e raised to x cube, that means e raised to 3x, this is e raised to 3x, but what is this? This is something less than e raised to 3x, sorry, e raised to x. This is e raised to x minus the first term, that is x minus x square by 2 factorial. That is what we removed from here. Here these 2 terms were missing, this term and this term was missing, right. So, therefore, we minus it. So, now we multiply, we get e raised to 4x minus x into e raised to 3x minus x square by 2 into e raised to 3x. Now, we are looking for the coefficient of x raised to 12 in this exponential x raised to 12 by 12 factorial in this exponential generating function, right. So, how do we know that? We have to take the coefficient of x raised to 12 in the expansion, x raised to 12 by 12 factorial in the expansion of this, then we have to take the coefficient of x raised to 12 by 12 factorial from the expansion of this, and then from this, and add them up. How will you do that? For this e raised to 4x it is easy, we have already seen that, right, because this will expand to 1 plus 4x plus 4x square by 2 factorial and so on. Now if you want x raised to 12 by 12 factorial, right, this will be 4x, sorry, 4 to the power 12, that is coming extra here, right, that will be coming extra here. So we have to take that 4 to the power 12. This will be the first contribution of this first term, and then this minus x 3x, what will be this minus x into e raised to 3x, right, e raised to 3x. Now note that when you expand it, this will look like 1, see this is x into 1 plus 3x plus 3x whole square by 2 factorial and so on. Now multiply by this thing, this will be x plus 3x square plus 3 square x cube by 2 factorial plus and so on, right. Now if you are looking for x raised to 12 by 12 factorial, the coefficient of x raised to 12 by 12 factorial, so you know that this 3 power will be, see somewhere here x raised to 12 will come, here you will see 3 raised to 11 then, right, because this x had taken that power of x by 1 extra, but below we will have a 11 factorial, not 12 factorial, because that x 12 became, actually x raised to 11 became x raised to 12 because of this multiplication by x, but what we want is only the coefficient of x raised to 12 by 12 factorial. So we introduce the 12 factorial in the denominator, but then we have to balance it by putting the same 12 factorial in the numerator. So cancel this off, so that will give you 12 into this 12 here, 11 factorial and 12 factorial, cancelling that you will get 12 into 3 raised to 11, right, that will be the coefficient of x raised to 12 by 12 factorial here. This is the contribution from this term. So we have a minus also of case, it's minus of this, right. Now last term is this x square by 2 into e raised to 3x, right. So now as usual this minus x square by 2 into e raised to 3x. If you want to find the contribution of the coefficient x raised to 12 from this, so now you know e raised to 3x will be 1 plus 3x plus 3x whole square by 2 factorial and so on as usual, but because we have to multiply this by x square by 2, right. So let us remember 2 separately, the x square goes and multiply here everything. So here this will become x square, this will become x cube, this will become see this will become 3 square into 3 square will come out, so x raised to 4 and so on. So when you are looking for x, the coefficient of x raised to 12 by 12 factorial, you should look at x raised to 12. So actually we are looking at x raised to 10 by 10 factorial, and you had this 3 raised to 10 here, right, which became 12 because of this multiplication by this x square, right. Now to get the coefficient of, so this is now this has become x raised to 12, x raised to 12 by 12 factorial. What we do is we introduce a 12 factorial in the denominator and introduce something here. Now cancelling off, we will have 11 into 12 left here, right. So we have 11 into 12 into 3 raised to 10 x raised to 12 by 12 factorial, but remember we initially had a 2 here, so this will cancel off, we will have 6, right, 11 into 6 into 3 raised to 12, 3 raised to 10 into x raised to 12 by 12 factorial. Now adding the contribution from each of this is minus of case the terms this and this, we will get the final answer. Okay, this was, I mean I am not really evaluating the final answer, it does not matter, we just wanted to illustrate how we can pull out the coefficient from each of these terms. Now yeah, that is it about, and next question is this: a company hires 11 new employees, each of whom is to be assigned to one of 4 subdivisions. Each subdivision will get at least one new employee. In how many ways can these assignments be made, right? So, not that. So, let us say subdivisions are called A, B, C, D. 11 people are coming. So, they are different people of course. So, now we can assume that we have positions. So, the first one, this is the second one, the new coming newly selected people, right, for the company. So, these are the 11 people, right. Now, we can write on top of them A. If the first guy is going to the subdivision A, we can write A there. If the second person is going to the subdivision B, we can write here. Third position can be written B, and if the third person is going to B, and so on. So, that is a sequence of letters, 11 letter word we are producing. The question is, how many 11 letter words can be produced, right, using these letters A, B, C, D, such that every letter appears at least once. So, in other words, in the function terminology, it will look like this. The people are written here 1, 2, 3, 4, 5, 6, sorry, 1, 2, 3 up to 11, and here the subdivisions A, B, C, D. Each person is assigned to a subdivision, right. Clearly, this is a function because each person is assigned to a subdivision, and same person is not assigned to more than one subdivision. One person can be assigned to only one subdivision, and each person has to go to a subdivision, right. So, this is a function from 11 to A, B, C, D, okay. And it is not just a function, we also have the constraint that each subdivision has to get at least one person. So, there is nothing like A does not get any pre-image in this function. So, it is indeed a on-to function. So, on-to function from 11 to 4, 11 size set to a 4 size set. How many are there? We have used the inclusion exclusion principle to count this. We can always ask this in a more general setting, but to illustrate the point we can take the example of 11 and 4, right. So, here we are trying to use this concept of exponential generating functions to get the answer. How will you do this thing? So, the first thing for subdivision A, we can give either one person or 2 persons. So, we write x for one person, x square by 2 factorial for second person, until we can have all the 11 persons, sorry, not possible, right. So, 10 up to 10% we can give it, no, not even that, but we do not mind, we will put it full because it is, because this will be automatically taken care of. So, we write the full infinite sequence here for each term, and we introduce a term for each subdivision. So, therefore, this raised to 4. We will say that this is the exponential generating function for the answer. So, I will continue this in the next class.